Our starting point is Cartesian coordinates, the xy plane. If we want to know the position of a particle in the plane, we can write it as a vector, x. We can write down the coordinates of the particle xy. We can also write down the vector in terms of an x component and a y component. X equals xi plus yj, where I is a unit vector in the x direction and j is a unit vector in the y direction. I and j are called a basis because every other vector in the xy plane can be made from a combination of these two. Because these two base vectors don't vary in time, and because they're at right angles, we can simply take the position and differentiate it with respect to time, component by component, to get the velocity vector, and then differentiate it again to get the acceleration. If x is the position, then dx by dt is the velocity. We also use a dot as shorthand for d by dt, so dx by dt is equal to x dot. d2x by dt squared, or x double dot, similarly is the acceleration. For example, if x has the coordinate ut vt minus a half gt squared, then we can just differentiate coordinate by coordinate and find the velocity and acceleration. X dot is equal to u, v minus gt, x double dot, the acceleration is equal to 0 minus g. What we want to do now is the same thing for polar coordinates. Polar coordinates are another way of representing where a particle is in the xy plane. This time we say that the position x of a particle is given by a distance r from the origin and an angle theta clockwise from the x-axis. The particle's in the same position, but we're using r and theta instead of x and y to describe this position. There are two slightly complicated things we need to know if we want to calculate position, velocity and acceleration in these coordinates. Firstly, we've got different base vectors. Instead of I and j, we have a unit vector in the radial direction, which we call er hat, and a unit vector at right angles to this, which we call e theta hat. So our position in polar coordinates is written x is equal to r er hat. It has magnitude r and direction er hat. So the position is simpler in polar coordinates than Cartesian coordinates, only one magnitude r and one direction er hat, instead of two, x and y, and two directions I and j. The difficulty comes when we want to calculate velocity and acceleration. We do the same thing, differentiate with respect to time, but this time our base vectors don't behave like I and j. I and j are constant, so when we differentiate them with respect to time, they go to 0. Er and e theta, on the other hand, depend on theta, which depends on time. They change direction as the particle moves around the plane. We can see how they do this if we write them in terms of Cartesian coordinates. We've seen that er hat is a unit vector in the same direction as the displacement of the particle. Trigonometry shows us that its x-coordinate is cos theta, and its y coordinate is sine theta. So this means we can write ER hat is equal to cos theta I plus sine theta j. Now we work out how it changes in time. But our position vector is not a function of time, it's a function of theta. Now we need to use chain rule. Differentiating with respect to time is the same as differentiating with respect to theta and then multiplying by d theta by dt, or theta dot. So, d by dt of ER hat is equal to minus sine theta times by d theta by dt, or theta dot, I, plus cos theta times d theta by dt, or theta dot, j. So we can simplify this by taking theta dot out, and we have sine theta I minus sine theta I plus cos theta j, all multiplied by theta dot. If we draw the other base vector, e theta hat, we can show that it's equal to minus sine theta I plus cos theta j. And then we can see that this term is equal to that term, so d by dt of ER hat is equal to e theta hat theta dot. And similarly, if we differentiate this term with respect to time, we get another relationship, which is d by dt of e theta hat is equal to minus ER hat theta dot. So we can use these results here to work out velocity and acceleration in polar coordinates. So differentiating with respect to time and using the product rule, we have dx by dt is equal to dr by dt times ER hat plus r d by dt of ER hat, or r dot ER hat plus r, and from here theta dot e theta hat. So we've now got an expression for the velocity in polar coordinates. We note that it's more complicated than the position. It's got a component in each of the directions. Finally, if we want to find the acceleration in polar coordinates, we just differentiate the velocity vector in the same way.